distributed group, which basically take funding from the University of Messina, Polytechnic Bari. And let me, first of all, thanks to the funding agencies. So thanks to the SPEDA-SPIN staff, we were able to take some funding from companies. And let me advertise our association, which basically try to exploit, to show to the community, which are basically the main results achieved in spintronics. And in particular, we are organizing a school in December, 13, 16, even if we already have the saturation of the students, if you want to apply, still you have time, and we ask it to the university to give a larger room to have 5 more students, so please do it. And also, last thing, I'm now from May, I'm associate editor of Physical Review Applied, and I'm trying to bring in this journal as much as possible papers on spintronics. So please apply, and we'll deal with these papers, yeah. Okay, so let me motivate why we really are interested in doing this computing stuff. First of all, we want to attack the IoT market, which is going to be really huge, and it is expected to be more than $1,000 billion in the next few years. And in order to attack this market, you can develop product or services. Spintronics is really useful for developing products because satisfy all these characteristics at the same time. And in particular, the cost of spintronic technology is expected to reduce a lot because of their ready development by the major fabs in the world. And basically, thanks to this, it is expected that spintronics is going to be basically available in the market in 2030. And to follow up this basically path, it is nice to develop some coprocessor which use spintronics, which can be integrated with CMOS technology either heterogeneously or monolithically. And basically, what we want to do is basically add some degree or some operation to support CMOS, where basically you need a lot of transistors to do, for example, strongly nonlinear operation, while with spintronics you need, for example, just one device. And before to go to the main part of the talk, which is probabilistic computing, let me show you what we have done for neuromorphic computing very quickly, and what we are planning to do. So first of all, I wrote a review with my team very recently, where we point out all the potential characteristics and application of spintronic diodes. And in particular, we got funded a proposal from the European Union where we have to integrate these diodes with CMOS technology. And one of the main devices we are using is the injection-locked spintronic diodes. And basically, we have an active device, so we have self-oscillation without any F signal. And then we have, in particular, in devices where you have strong nonlinearity, and then you work in the injection locking region near this nonlinearity, you get very high sensitivity, and which has been optimized thanks to a funding from the Italian Space Agency that they want to use this device for space application. And also recently, from the group of Suzuki, actually they combining the injection locking with this bolometer effect, they got 4 million megavolt over watts. So this is absolutely an impressive number. So you can work with input power below 0.1 nanowatts, basically. All right, so the main idea is to use these devices for neurons. So the main idea was established a few years ago. We used the ascending branch of this resonant curve to basically reproduce the ReLU activation function. And this has been tried in a very simple network where you have just fully connected layers. And of course, because we want to use this ascending branch, we want to develop devices where the ascending branch is as large as possible. And this is actually the experimental work we did together with Zhongmin Zheng a few years ago. And using this, basically this curve, we developed a more complex network where we have convolution. And this is the activation function of the neurons in the fully connected layer. So what we did is basically take the experimental data, and this is actually the curve. But in order to, and this actually worked very well when all the devices are the same. But basically, by macromagnetic simulation and changing the parameter, we saw that this curve can be rotated by plus or minus 5 degrees, as you can see here. And then we did a sort of transfer learning from software network to hardware network. At the end, we are trying to see what's going on when you do this. And without an additional learning, we evaluated the accuracy by considering all the devices different according to this law. And this is actually the results we get. So the conclusion here is that at least for this type of variation here, which is very reasonable, even more than what you expect, actually the transfer of learning from software to hardware is pretty robust if you use spintronic devices. Of course, as we learned this morning, you can do very, very interesting thing with passive diodes, as explained by Alicia in a very inspiring talk. And also, an activity which has been led by Vito in our group actually is to demonstrate that we can use also this diode, injection locked diode, for making analog multiplication. And the main idea is beyond the degree of match, and we call this degree of rectification. So basically, we have a function, P, which has an input-output relationship, which can be described by a parabolic function. And by using some measurement of this function, which in the case of diode is directly the voltage, so it's going to be very easy to use instead of what you can use for oscillators, give you the multiplication. So we have either experiments, then theoretical analysis to see, of course, which is what we can achieve. And actually, using this formula, as you can see here, if we expand near the maximum this cosine, we can have a sort of parabolic description of this voltage versus current. And these are the results we achieved by comparing the ideal multiplication with the simulation data or with experimental data. So it's pretty much good. And also, we did a sort of analysis for convolutional neural networks. And in particular, this is the main result. So where we saw that the correlation number, which basically tell you how much is close the convolution of one image with a specific filter, is basically here. As you can see, it's close to 1 in the case of experiment, and we predicted that in theory you can achieve even much better performance. And even another advantage of this approach is that you can do this very quickly. So this is not optimized for basically making multiplication, so you need few nanoseconds. But there are oscillators where you can work frequency which are much larger, and then you can do the same operation in a sub-nanosecond scale. And what we are doing now, but I will not talk too much about that because this needs a totally different topics, is how we can transfer we can deploy a neural network which is smaller, implemented in spintronics, starting by a bigger network by using knowledge distillation and dark knowledge. So this is a path that we want to do, and we are developing right now. All right, so in terms of basically synapses, we basically want to show how we can use these antiferromagnets. In particular, from what I understood, we can identify two types of switching in these antiferromagnets. One is basically the one in copper manganese arsenide in this pioneering paper, where basically you have that the resistance states depends on the number of passes. And the other one is the one taken by Takahiro, so basically where the state of the resistance is not dependent on the number of measurements, but it's just dependent on the current you apply. So these are two different types of resistors. This material, anyway, are not so compatible with CMOS technology. So our research was to try to get the same results in different materials, which are compatible, and then also which are not extended, so which has been scaled. In particular, we used micropillar for this first experiment. And basically, the material here is platinum manganese, which is used already in MTJ, so it's compatible with the process you have. And the main results here is that we achieve a state which is independent on the number of passes you apply, but just dependent on the current you apply. This is pretty useful for making synapses. The main, in order to have this state, actually we need this easy plane anisotropy, and we need to stabilize the system in a non-uniform ground state. In particular, we need to have the system in a configuration where you have domains, and the domains are characterized by vortices and antivortex. So when you apply the current, actually you don't move the domains, but what you do, you enlarge and expand. And so the pinning can basically block. And this is qualitatively different from what you get when you stabilize basically ground state with just easy plane anisotropy or the Olszewski-Mourier interaction, as we systematically study in this paper. So what is important is that you go in a metastable state. And of course, some people say that you can have electromigration. So in order to fix this issue, there was this nice paper by the group of Idehono where they show the image of the same material. And also we developed a technique to make differential measurements. And actually, these are the results we got. So we measured the branch where you have no pillars, the branch where we have pillars, so we compare. So in order to be sure that what we see is something which is related to the antiferromagnetic states. And here, actually, the origin of the switching there is given by shifting on domain walls. And in this case, because we have cubic anisotropy, we have coexistence of different domains which moving, they basically give you this signal. All right, so let's go to one very hot topic that we are really dealing with this. And I want to talk about probabilistic computing right now. So why we are so interested in this probabilistic computing? So the main reason is that we can do Ising machine. So actually this means that because Ising machine are NP problem which basically can solve NP complete problems, actually we can map every NP problem in an Ising machine. So solving Ising machine means we can solve almost all the NP complete problems. Our contribution in this field are basically two recent papers, one done basically mainly by my students, Andrea, where we demonstrate, we combine probabilistic computing with invertible gate side parallel tempering. And one has been done together with Keren Kamsari, where basically we try to move this in CMOS, so implement all this technique in FPGA. So, but let's start with the very simple definition of Ising model. So actually, what we have to do is just to find out the minimum of this Hamiltonian. And actually, you have the spins. So actually, which are the spins M which give you the minimum in the energy landscape of this Hamiltonian? So mind that the spins can be just 1 or -1. So this is a discrete energy landscape. So one way to solve this is just by annealing. So what you do, basically, you increase the temperature. Then you reduce a little bit the temperature slowly, and then the system evolves according to some time to the minimum. So if the velocity of reduction is not so high, actually you get absolutely the minimum. It's a very simple annealing process. So you're gonna go too much far for this. It's not very scalable. And then actually we implemented the parallel tempering on this. So actually we created different replica of the problem. Each of the replica works at fixed temperature. And then they interact with some rules. For example, we implement like several rules to make this replica interacting. And one of these is basically, at some point, we have some deterministic switching of the replica among different temperatures, where around the energy becomes smaller than the one at the closer replica. And this actually basically following this simple rule. But this is just one of the technique we implemented. And so one way to solve Ising machine is probabilistic computing, as I said also in the talk, in the first talk after the coffee break. Basically, thanks to a suggestion of Feynman, we can try to implement this probabilistic computer. And the main difference between this computer is basically in the element which take the information out. In particular, if we have standard technology, basically we have 0, 1, and then we need to apply an external input to change the state. In qubits, you have all the state overlapped. So when you apply an external input, basically you select the state which is more compatible with that input. For p-bits, actually, all the p-bits jumps between 0 and 1 with 50% probability. And then when you add the input, actually, you select the probability of the p-bits to stay in one state or the other. For example, we already with Zhongming developed the hardware to make actually these p-bits directly from MTJ. And what we can do with these p-bits, actually? So one very interesting idea was proposed by Kamsari, and the key idea is the invertible logic gates. But in order to implement this, we need to have a tunable p-bits. So we need to control the probability by an external source. In this case, he proposed a 3-terminal device. So you apply current, you can tune basically the probability between this point and that point. So this is one way to do that. But also you can do in 2-terminal device by using an external field or voltages. And actually we are working basically in 2-terminal device right now. So once we have this tunable basically p-bits, we can implement the invertible gates. And the algorithm to calculate these gates basically is need an asynchronous update. So it means if I have 5 p-bits, I can just, one iteration is basically given by the file calculation. So I calculate one pip bits, then update, another pip bit. So it's a sort of sequential update. So this actually slows down a lot the way you can use this technology for solving very huge problem, because think you have like 1,000 or million of pip bits, right? It's going to be really complicated. But anyway, so with these ingredients, we can implement basically logic gates which are invertible, means we bias the output to force the output to 1, and then actually the inputs, basically in this case, will stay to 1 because this is an AND gate. In case you force the output to -1, actually, as you can see here, the state of the inputs jump between 0, 0, 0, 1, 1, 0 with equal probability. So this is a sort of basically invertible gates, not in functional sense, but in a relational sense. Okay, so of course now we have the background to create all the gates, all the circuits. And we also, in particular, when we have gates which share the pip bits, we are able to combine properly these pip bits and create a smaller matrix. So we are able to compact basically the problem. But now that we have all this, what we have to do? What do we want to do? We want to do something which can be very impactful, which is the solution of any combinatorial optimization problem. So this is the procedure to do that. You have a company, give you a problem, which is mapped in one of these, and then you solve it, give you the response of the problem, and then the company use the solution. So why we need to solve this problem? The main reason is that we can basically reduce the carbon footprint on that. Because typically this problem are logistic, and then you can really reduce either the cost for the company, but the impact on carbons. Then actually we can have different problems. Today you saw this traveling sales problem. Now let me focus on MaxSat problem. Okay, so MaxSat problem, can be written in a Boolean formula. So you have different clauses here, which combine with, in this case, or different variables. And the objective of this problem is to find the maximum number of clauses which are satisfied at the same time with a specific combination of the state of the variables. In particular, the cost energy which is used by informatics people is the number of clauses which are not satisfied, okay? So, actually, you can clearly see here that this problem can be written in terms of logic gates. In particular, this is the instance which comes from a company, which is linked to some problem they have to solve. Then we map this in a circuit, like that. And then actually, once we have the circuits, we can create the Ising model by mapping, by substituting these gates with invertible gates. Then we create the Ising J matrix and H matrix, and then we combine properly together to have the final one. And then we apply an annealing process to solve this problem. And in particular, with parallel tempering, for example, this is one problem which has around 2,000 pip bits, which is a pretty huge problem. And these are the number of iterations we get with the very simple parallel tempering approach, where we have just 4 replica of just 4 replica of the problem itself. And actually, of course, we do this several times because it's probabilistic computing. And then actually we compare 5 replica with 4 replica and so on. And actually we basically give the meaning to this actually. In order to have, to be very well, to work very well, actually the temperature should be selected in order that the energy cost between different replica overlap a little bit so they can communicate. Otherwise it's like you have 4 replica which work independently each other. And I want to highlight that this is important, this for us, because this algorithm can be parallelized. So actually, this is the first step toward parallelization. And with this technique, we were able to solve, let's say, MaxCat problem. We went much more behind the state of the art, and also in terms of numbers of nodes, and also the weighted MaxSat, which is which is very important for a lot of companies working in logistics. All right, So now all of this has been done in software, and now we want to see if we can do something more serious in hardware. In particular, in order to do that, we tried this with FPGA. It's not working. So in order to improve the performance of FPGA, we introduced the concept of sparsification. So actually, we reduce the number of neighbors in the circuits by adding degeneracy in the circuit. So somehow we increased the number of bits which describe the same problem instead of reduce it. And when we do that, actually, we have very, very sparse graph. And then we can apply graph coloring algorithm to identify basically all the groups in this graph. And then we can update each of this group, which, for example, they can have different color, so simultaneously. So basically, in this way, instead to update one p-bits at a time, we can update a group of p-bits at a time. And at the end, this gives you a significant improvement. And before to go to the result, let me see how it looks like basically a sparsified graph. So this is the starting graph for 32-bit factorizer. And this is what's going on with the sparsification techniques. So you see you have just p-bits which communicate with 5 neighbors. So at the end, you need just 5 iterations to update all the network instead than like 2,000. And this result has been published in this paper very recently. And this actually are some calculation we did either with MaxSat and with 32-bit factorizer. And this is the main results of the work. So where basically we beat the state-of-the-art solver for MaxSat for solution up to 95% of the optimal one. Still, we are working on to beat this solver to find the 100% solution. But we are developing this, and we are on the direction. Okay, so one way to speed up the calculation, as I told you, is this sparsification technique. Another way to do that is basically taking advantage by the idea of physics, so where you have a lot of bodies, and they interact asynchronously. And then means that you have no specific clock which say when you have to change your state or not. So in order to reproduce this in FPGA, what we did is we used these ring oscillators, but we can do this also with spintronic oscillator, where you can tune basically the frequency. And these actually the clocks which are observed basically while updating all the p-bits. And when we are going to compare all the results together, what we saw is that still the synchronous Gibbs update works very well, better than all the other ones right now. So we need to find something which is better. And now come in the game spintronics with the devices which has been sent to Kerem Kansari by Shu Hunke. And basically here, instead to use ring oscillator to make basically the update, we use random magnetic tunnel junction. And this actually gives you the timing where the p-bits of a specific group has to be updated. So this is the first step to move the probabilistic computing toward to move spintronics into probabilistic computing for making some calculation with invertible gates. The other one is basically based on previous results where you have this p-bit which work a nanoscale second. And in particular, what we have done, we have studied micromagnetically and with microspin approximation this system. And we did a massive study, and then we have identified which one is the best configuration. Still, we are working on the experiments right now. And what we did is we create the Ising machine with magnetic tunnel junction, which has these characteristics. And we apply this to solve MaxSat problem. And surprisingly, actually, if we convert the iteration with the time scale, we saw that we are able to solve this problem, which is around 800 p-bits in 50 nanoseconds. So which is something which goes much more beyond the FPGA. So I want to just highlight here is that probably we are mistaken here for, let's say, 2 orders of magnitude. So instead to be 50, this is going to be 5 microseconds. This can be, of course, right? At the end, if we compare with FPGA, is 5 milliseconds. So at the end, still, if we have 2 orders of magnitude, we go 2 orders of magnitude slower, Still, we have 3 order of magnitude, we got 3 order of magnitude faster than FPGA, which is the current state of the art. Okay, so very quickly, a few minutes, just I want to show you 1 minute. I want to show what we've done with basically factorization, which is not optimization problem, is basically a problem where you have just one minimum. All the other solutions basically are not important. And the objective is to find, basically, to solve this RSA problem. So with this, actually, we will really bring this ISIM model, ISIM machine to the attention of all people. So we are working on this. And of course, we want something which, in terms of velocity, is going down, is below this state-of-the-art algorithm. And just to show you how we solve it with invertible gates, which is different algorithm than the one presented in the Nature by other groups, actually, we clamp the output, and then we check basically which is the configuration which satisfies the output. And then actually these are the output bits where we say that this is the output or not. And with parallel tampering, we were able to factorize 25 bits. Then we moved this in FPGA, 18 bits without any sparsification. And now with sparsification, we are able to go to 32 bits. And this is just the beginning, because we are now moving to 50 bits and so on, and this is going to be slowly, we will reach RSA. All right, so this is just a summary of the results, and let me thanks again the funding agencies.